In this video, we are going to be talking about stereoisomerism in alkenes and Bredts Rule. So, alkenes do have stereoisomerism because there's not free rotation about a double bond. So, this double bond holds those carbons where they are, and this carbon cannot freely rotate like they do in single bonds. So, with that being said, cis 2-butene, cis meaning same side, the two substituents of this double bond are coming out at the same side, is the stereoisomer of trans 2-butene, trans meaning opposite. So if I were to draw a line down the middle of this double bond, you can see that this methyl is going up and this one is going down. But for this one, for cis, they're both going up. And also, I wrote a note down here, cycloalkanes fewer than 7 carbons can only be in the cis conformation. That's not super important to this video, but it is something that you need to keep in mind. So now we're going to talk a little bit about Bredts Rule. And the wording of this is confusing, but don't worry, we're going to go into it a little bit deeper so that you fully understand what this means. So the definition of Bredts Rule is that it is not possible for a bridgehead carbon of a bicyclic compound to possess a carbon-carbon double bond if it involves a trans pi bond being incorporated into a small ring. So let's break that down a little bit more. So first of all, we have bicyclic system. This is a bicyclic ring. There's another video on bicyclic compounds that you probably need to watch if you don't really know what this is. And then we have bridgehead carbon. So remember that these right here are the bridgehead carbons. It is where the two rings come together. It is specifically the carbon that connects the two different rings. And then we have a carbon-carbon double bond right here. So these are the pieces being incorporated into this. And also it says a small ring, and so small is being considered more than smaller than 8 members. So in this case, the big ring only has 6 carbons, so that's considered a small ring. All right, so let's go back to what this is saying. It is not possible for a bridgehead carbon, so these carbons right here, of a bicyclic system to possess a carbon-carbon double bond right here if it involves a trans pi bond being incorporated in a small ring. So if we look at this double bond right here, remember the difference between cis and trans. If I draw a line through the middle of this double bond, we have one thing coming off of it going up, and then the thing over here is going down. So this right here is a trans double bond. And Bredts Rule says that this is not okay. If that double bond is, if one of the carbons of the double bond is a bridgehead carbon, it cannot be trans if it is smaller than 8 members, which this is. So if you have a big molecule where the big ring is 8 members or larger, it is totally fine for this bridgehead carbon to be with a double bond. But since this is 8 members or smaller than 8 members, so specifically 7 carbons or less, it cannot form a trans double bond with this bridgehead carbon right here. So now we're going to talk about which one is a Bredts Rule violation. So remember what that means. It's talking about a bridgehead carbon possessing a double bond with smaller than 8 members. So take a second, pause the video, and see if you can figure out which one is a Bredts Rule violation. So it's going to be the top left one here. Let's go through the ones which are not Bredts Rule violations first. The reason that this is not a Bredts Rule violation is because this double bond is not containing the bridgehead carbon. These are not bridgehead carbons. Actually, I'm going to put an X on those. For a Bredts Rule violation, it must possess one of these carbons with the double bond. This one is not right because it is a bicyclic compound, but it does not have bridgehead carbons because it doesn't have this bridged portion. This one has the bridged portion, and it does contain a double bond on the bridgehead carbon, but let's count the number of carbons in the big ring. It has 1, 2, 3, 4, 5, 6, 7, 8. And remember, Bredts Rule says that 7 or less would make this a Bredts Rule violation. So it is totally fine that this right here is trans because it is larger than 8 members. So this one right here is going to violate Bredts Rule. So now we're going to talk about E and Z designations for double bonds instead of cis and trans. So when you are naming an alkene using IUPAC rules, they are going to use E and Z instead of cis and trans. And they correlate with each other, so Z would be the cis conformation and E would be trans. So how do we know if it's E or Z when there are more than 2 substituents? So here, this alkene has 3 major substituents. So we're not including this hydrogen right here, but it has this ethyl right here, a fluorine, and then it has an amine group. So when it only has 2 substituents on either side, you can easily tell whether it would be E or Z, but in this case it has 3. And so now we're going to talk about how to determine whether it's E or Z or cis and trans. So deciding E or Z. Step 1 is to assign priority to the 2 groups on each side of the double bond using IUPAC stereochem priority numbering. So if you don't know what this means, go back and watch the videos on stereochemistry, and you're numbering these the exact same way as you would for normal stereochem. And so this means that you're going to use the highest atomic number to get priority. So first step is draw a line through the double bond, look at either side of it, and then over here we have 2 groups, and so we're going to number them based on priority. So this fluorine is going to have a higher atomic number than this carbon right here, and it goes the same way. If these are the same, then you would go to the next atom over. But in this case, fluorine is a higher atomic number than carbon. So this would get priority 1 and this would get priority 2. Nitrogen also has a higher atomic number than hydrogen. So this amine group right here, this should be an H2, gets number 1, and then this hydrogen right here would be number 2. So step 2 is to compare the number 1s. So you're going to look at both sides and look at the number 1s. In this case, if you split the double bond, both number 1s are going in the same direction. So in this case, they are on the same side, and so this would be a Z configuration. And I wrote, if they're on the same side, then it's Z, and if they're on opposite sides, then they're E. In the example above, number 1s are on the same side of each other, so it is in the Z configuration. I hope you found this video to be really helpful. The concepts and information presented in these videos will be true no matter what Organic Chemistry 1 class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.